Today we're talking about chords and arcs. We want you to learn to use congruent chords, arcs, and central angles in circles, and recognize the properties of lines going through a center of a circle. So we've got a lot of different theorems that we're going to be talking about today, and there's a lot of different problems that you'll be able to solve after we're done with this video. So let's first go with the definition. A chord is a segment whose endpoints are on a circle. So if we are talking about something that does not pass through the center of the circle, or even something that does, like a diameter is the greatest length chord that we could have. Okay, a radius though is not a chord because its endpoint, only one of them is on the edge of the circle. So those are a couple different things that could be chords. So let's talk about theorem 11.4. Within a single circle or in two or more congruent circles, we're going to have congruent angles have congruent chords. Okay? So say we are looking at just one circle, and I've got X and X here, right? Central angles have congruent chords. That means that the lines that connect these two, since the angles are congruent, the chords will be congruent to each other. Okay? If you saw that in two circles, it would just look like this. So this chord will be congruent to that chord. Okay? Congruent chords have, and this is the converse of the previous statement, have congruent arcs. Or no, sorry, it's not the converse, the third one's the converse. So the congruent chords have congruent arcs, and the arc is what we're talking about is the distance around the circle from here to here, from here to here would be congruent. Here to here and here to here would also be congruent. And then congruent arcs have congruent central angles. So the congruent central angles are related to the congruent chords, which are also related to the congruent arcs. And then if you can show that you have congruent arcs, you know that you have congruent central angles. So it's kind of almost a transitive property thing with a converse built into that. So we have the congruent central angles create the congruent chords create the congruent arcs, and congruent arcs have congruent central angles. Okay, so it's kind of that whole circular thing going on here with that. Now let's talk about theorem 11-5. And I'm going to make this a little smaller so we can see this. Within a single circle or in two or more congruent circles, chords that are equidistant from the center are congruent. Now let's think about what distance from a center means. That's distance from a point to a line. So if the distance from here to here, and that's the perpendicular distance, is the same as the distance from here to here, from the center to the chord, if that distance from the center to the chord is the same for both of those chords, then my chords are congruent to each other. Okay? The converse of this is that congruent chords are also equidistant from the center. Okay, so their distances are the same. So this is the converse of that. Okay? So I hope that helps you. So with this theorem that we know that if we have congruent chords within a circle, they must be the same distance from the center. So that's going to help you when you're looking at different parts of the circle. If you recognize that relationship, it's one more piece of information that you can know about that circle and finding missing lengths. Now here we have a few more theorems. Theorem 11-6 says, in a circle, the diameter that is perpendicular to the chord bisects the chord and its arcs. So, with this situation, so here we have a chord, and we have a diameter that's perpendicular to that chord. So it bisects the chord and its arcs. So those two little arcs are congruent to each other as well. Now the converse of this is called theorem 11-7. In a circle, if you have a diameter that bisects a chord, and that chord itself is not a diameter, then okay, so here we have a diameter bisecting a chord. If you have that situation, and this chord is not a diameter itself, then this is perpendicular. Okay. Now, why do we specify that that this chord that it bisects can't be a diameter? Well, here's the situation with that. If this were to bisect another diameter, say this diameter here, there's no control over whether that angle is a right angle or not, because there's infinitely many diameters that it could intersect and bisect. Okay, so that's why that stipulation is in there, that the chord that it bisects cannot be another diameter. Now let's talk about theorem 11-8. In a circle, the perpendicular bisector of a chord contains the circle, and this kind of falls in line with these other two theorems here, because theorem 11-6 says the diameter that is perpendicular to a chord bisects it, right? And so a diameter goes through the center of a circle, right? So in a circle, the perpendicular bisector of a chord, right, contains the center of the circle. Okay? And that kind of is almost a corollary of 11-7 and 11-6. Because 11-7 says the diameter, which contains the center of a circle, that bisects a chord is perpendicular to the chord. Okay? So that it's almost a corollary rather than a theorem on its own. Okay, so let's look at this example. Here we have a couple dimensions put in and a couple dimensions not put in. Okay, so we want to find what are x and y. Well, we know that x should be 10 centimeters, right? And then since the distance between these two chords is identical, then the chord lengths are identical, so this segment should also be identical. So this y should equal 10 centimeters. Okay, now we're going to do a lot more problems with these theorems in class, so hopefully you guys can just kind of read through them, look at some of the problems in the book, try to get a good handle on that before you get to class, and then you'll have some questions that you can ask when you get to class. So I know this is a lot of theorems thrown in so far in this first couple of lessons, but I think that hopefully we can help that make sense for you in the end. Okay, so here's what we've learned. We've learned what a chord is. We've learned that chords that are equidistant from the center of a circle are congruent, and we've learned that if two chords are congruent, they must be equidistant from the center. We've learned that diameters that bisect chords are perpendicular to the chords, and that if a diameter is perpendicular to a chord, it must bisect it. And we've learned that the perpendicular bisector of any chord contains the center of the circle, because why? It's a diameter. Okay, so hopefully this is a nice, neat way of saying all these things, and you can sort of start seeing these relationships in your head and memorizing what they look like so that you can recognize them when you see them in different situations. That's it for today.